Hey everyone. So, what if I told you there's a computer chip out there that seems to, well, to break the laws of time? A machine that can do a job in just a few minutes that should take longer than the entire age of the universe. It sounds like science fiction, but it's real. And today, we're going to figure out exactly how it works by diving into a concept that literally bends the fabric of information itself.
First, just take a look at this number. That is 10 septillion. And that's how many years one of the world's most powerful supercomputers would need to crank through one very specific, very tough calculation. I mean, it's a number so big it's hard to even wrap your head around.
Okay, but get this. That exact same task was finished by Google's Willow quantum processor in just 5 minutes. So the big question is, how? How on earth do you compress 10 septillion years of work into 5 minutes without shattering the ultimate speed limit of the universe, the speed of light?
Well, it turns out the answer has nothing to do with going faster through space. No, it's about something way more profound. Something that actually changes how we think about what information and even work itself really are.
And this right here, this is the key. The quantum ship isn't just doing the same old work, only faster. It's performing a totally different kind of work. It isn't breaking the rules of physics at all. It's just using those rules in this really clever new way that basically reorganizes the flow of cause and effect.
So how does it do that? How do you just reorganize causality? To get that, we need to peek behind the curtain into this invisible realm where quantum computers do their thing, a place where, the rules of our everyday world don't really apply.
And here's the fundamental difference. A regular computer bit, it's like a light switch. It's either on or it's off. It follows one single path at a time. But a quantum bit, a qubit, it uses this incredible property called superposition. So think of it less like a switch and more like a dimmer dial. It can be on, off, and every single possible value in between, all at the same time. This lets it explore a massive number of possibilities simultaneously. And all of that simultaneous exploration, well, that's what we call virtual work. It's this enormous calculation that's happening in the background, in this hidden quantum state space, long before we see a final answer. This is where those septillion years of classical computing get squeezed down. So, what's powering all this virtual work? What's the engine driving this incredible computational feat? The answer is actually beautiful, and it's simple. It's light, but maybe not in the way you're thinking. We're talking about something called virtual photons. Now, these aren't particles of light zipping around inside the chip. Think of them more like the fundamental vibrations of the electromagnetic field itself. They are the messengers, the little workers, carrying information back and forth between the qubits, and they're the ones doing all of that immense virtual work.
I love this quote because it just captures the idea so perfectly. At the deepest level, all computation, whether it's on your phone or in a giant supercomputer, is basically just the act of telling light what to do, of structuring its behavior. Quantum computing just does this on a scale that is, frankly, mind-bogglingly complex. Okay, but wait, if all this virtual work is totally invisible, how do we even know what's really happening? Is there any way to actually measure it? Well, the answer is yes, and there's a new metric that's been developed to make this really abstract idea totally concrete.
We can measure it with something called the virtual work constant, or KV for short. The easiest way to think about KV is like a performance score. It's like MPG for a car. It tells you exactly how good a quantum processor is at turning the raw potential of its internal light cycles into useful, structured virtual computation.
So how do we figure it out? The ingredients are actually pretty intuitive. First, you look at the number of qubits. Those are your workers. Then you measure their speed, which is called the layer rate. Then you factor in how well they're all connected through entanglement. That's that spooky quantum link where different qubits act like one big coordinated team. And finally, you just compare all of that work they're doing to the system's total potential, its light cycle capacity.
So let's actually walk through it for a chip like Willow. First, we figure out the total number of light oscillations happening every second. That's its maximum capacity. Then, we see how many virtual paths its entanglement is creating. That gives us the virtual work rate, which, you can see, is just a ridiculously huge number of events per second. The last step is simple. Divide the work that's actually getting done by the system's total potential.
And what do you get? A KV value of around 107. Now what does that even mean? It means that for every single tick of the clock, every single oscillation of light inside that chip, the system is performing over 100 coherent, useful virtual calculations. It is an absolutely incredible amplification of work.
And now we get to the big reveal. How does all of this connect back to our original mystery about time? This is where quantum computing gets really wild and hooks directly into one of the most famous theories in all of physics.
This right here is the core idea. We all know Einstein's theory of relativity, right? As you get closer to the speed of light, your velocity literally bends the fabric of space-time, and for you, time itself slows down. Well, quantum computation does something amazingly similar. High quantum coherence, that dense, coordinated virtual work, bends the fabric of informational space, and that compresses all that work into a much shorter amount of our time.
This just puts it so beautifully. Relativity gives us the rules for moving through physical space. Quantum mechanics, seen this way, gives us the rules for moving through the space of all possible answers. They're like two sides of the very same coin.
So when you boil it all down, the quantum speedup isn't about speed at all. It's a geometric effect. It's geometry. Just like a massive star's energy density creates gravity by literally curving spacetime, the dense, coherent energy inside a quantum computer curves the geometry of information, creating a shortcut for the calculation to take.
Okay, let's zoom out for a second. This new way of thinking doesn't just explain how a quantum computer works, it hints at a much deeper connection between gravity, information, and maybe the very nature of reality itself.
Look, this KV constant isn't just some weird philosophical idea. It's a seriously practical tool. For one thing, it gives us a universal ruler, like a horsepower rating, so we can finally compare different quantum machines apples to apples. It also shows engineers exactly which knobs to turn, like qubit connectivity, to make their hardware better. And most profoundly, it's a real mathematical bridge between the world of quantum information and the world of Einstein's relativity. And this leads to a pretty stunning thought. It suggests that every time scientists fire up a quantum computer and measure its efficiency, they are, in a very real way, running a tiny, controllable experiment on the nature of quantum gravity, which is one of the biggest unsolved mysteries in all of physics. This table just synthesizes the whole pattern we've been talking about. On the cosmic scale, you have mass energy creating gravity, which curves the medium of spacetime. And on the quantum scale, you have coherent light energy creating computation, which curves the medium of information. It's the same principle, just playing out in different arenas. Energy density shapes the geometry of cause and effect.
And that brings us to our final thought. We've just seen how the same fundamental law shapes everything from galaxies to computations. It's a law that connects energy, geometry, and the flow of time.
So the question we're left with is, now that we're starting to learn the rules, what else can we build by learning how to bend the fabric of reality itself?